Section 5.9.3 Solving a general polyalphabetic cipher. A general polyalphabetic cipher can also be done using a tableau. The rows of the tableau can be mixed according to any scheme, independently of one another. It is worth noting that the number of rows need not be the same as the number of columns. For computer ciphers, it can be valuable to make the tableau 256 characters wide and 512 rows deep, so that each ciphertext character appears twice in each column. That will make it difficult for an opponent who has obtained a ciphertext and its corresponding plain text to determine the key. Here is a partial example of a 100-row tableau. This tableau would be used with a numeric key where 2 decimal digits would be used to select the row for enciphering. A 20-digit key would produce a polyalphabetic cipher whose period is 10. Solving a general polyalphabetic cipher is very like solving a monoalphabetic cipher. You begin by taking a frequency count and making a contact table for each column. In this case, the contacts for column C will be in columns C-1 and C+1, wrapping around from the rightmost column to the first column as needed. There will be fewer occurrences of each letter in one column, so you need to make inferences from less data. This takes a lot of inspired guessing, which comes from experience. Let's begin with this polyalphabetic ciphertext. A quick examination of this ciphertext shows 2 long repeated sequences, YSUZONSOO at positions 13 and 93, and SNZYYZK at positions 39 and 124. In both cases, the distance between the 2 occurrences is a multiple of 5, confirming that the period is 5. These long repeats probably represent common words or phrases, or words specific to the subject of the message. The contact charts for each of the 5 key letters follow. To make it easier to explain the deductions, I will tag each ciphertext letter with a digit specifying its alphabet number. So C1 would mean the ciphertext letter C in alphabet 1, that is, enciphered with the first letter of the key. H3 would mean ciphertext letter H in alphabet 3, using the third letter of the key, and so forth. Recall that letters with many different contacts on both sides tend to be vowels, while letters with fewer distinct contacts tend to be consonants. Based on these contacts, we can tentatively identify as vowels G2, K2, O2, P2, H3, K5, and as consonants R1, Z1, K3, N3, D4, S4, O5, U5. Based on its high frequency, S4 probably represents plain text T. You proceed exactly as you did for simple substitution. You update the contact charts to show those letters that have been identified as vowels and consonants, and you also write the ciphertext with the vowels and consonants marked. You use this to refine and repair the vowel/consonant identifications and to identify individual letters. I will not repeat all the steps taken in section 5.1. It is the same logic, but the incremental steps are smaller and more numerous, with more backtracking. The general polyalphabetic cipher is rated 3. Section 5.10 Autokey. You may recall that I said in section 5.9.2 that Vigenère made 2 improvements to the Belasso cipher. The first improvement was placing the guides around the edges of the tableau to produce a mixed alphabet. The second improvement was the autokey. The autokey uses the plain text of the message as a key to encipher the rest of the message. An early version was invented by Italian physician/mathematician/astrologer Girolamo Cardano. In Cardano's system, each letter was enciphered using itself as the key. This only works if you have an alphabet with an odd number of letters. Using the English alphabet of 26 letters, an A would produce an A, and an N would also produce an A. So the intended recipient would have to figure out which was meant. Even with an odd-size alphabet, the Cardano auto key merely produces a simple substitution. Fictionnaire improved upon the Cardano method by using a lag. Fictionnaire used a one-letter key to encipher the first letter, used the first plain-text letter to encipher the second letter, used the second plain-text letter to encipher the third letter, and so forth. In modern practice, a keyword is used to encipher the first group of letters, then that group of plain-text letters is used to encipher the second group, and so on. This example uses the key sample with the Balasso tableau, that is, unmixed alphabets. With unmixed alphabets, decryption is straightforward. The index of coincidence, described in section 5.7, can be used to determine the length of the keyword. The index is often dramatically higher when the ciphertext is offset by a multiple of the key length, like this. Suppose you have found that the keyword has 6 letters. Try each letter of the alphabet for the first letter of the key. Start with A. Since the first ciphertext letter is L, the first plaintext letter must also be L. This will also be the key for the 7th letter of the message. Since the 7th ciphertext letter is X, the 7th plaintext letter would have to be M. Proceeding this way, each guess for the first key letter gives you the corresponding 1st, 7th, 13th, 19th, 25th, and 31st characters of the plaintext. That is, it gives you every 6th plaintext letter. There are 26 sets of letters, one for each possible key letter. Some of these sets of letters will have normal English letter frequencies, some will be implausible. Repeat this for the second key letter. Each guess for the second key letter gives you the corresponding 2nd, 8th, 14th, 20th, 26th and 32nd plain text letters. Now take the 5 most probable choices for letters 1, 7, 13 and pair them up with the 5 most probable choices for letters 2, 8, 14. This will give you 25 sets of bigrams. Some of these will be highly likely, some will be implausible. Take the 10 most plausible of these and pair them up with the 5 most likely choices for the third key letter. This will give you 50 sets of trigrams. Choose the 10 most reasonable of these and pair them up with the 5 best choices for the fourth key letter. By this point, some plaintext words will start to appear, and the correct choice of key letters will become obvious. If you are doing this by computer, skip the bigrams. Simply try all 26 to the power 3 combinations for the first 3 key letters and go straight for the trigrams. Then repeat this for the second 3 key letters, that is, key letters 2, 3 and 4. The most likely choices for the first 3 key letters and the second 3 key letters will overlap. The same will happen with the third and fourth sets of key letters. This will rapidly narrow in on the correct keyword. Fictionnaire autokey using standard alphabets is rated 3.